the One World Combinatorics on Words seminar. Our speaker today is Matthieu Rosenfeld, and he's going to speak to us about reconstructing words using queries on subwords or factors.
So I will be talking about reconstructing words using queries on subwords and factors. And this is joint work with Gunnar Richomme. So the first thing I will need to do is to define the problem I want to look at. Okay, so let me just remind some definition that we agree even on the most basic stuff. So I will have an alphabet, which is just a finite set of letters, and a word is just going to be a finite sequence of these letters. Okay, and just also to agree on this notation, so for every letter A and integer J, when I write A to the G, I mean A G times. So for instance, A to the 5 is just A. And this would be true as well for words. So if I write AB to the 5, it would be AB 5 times. Okay, so what the problem I want to look at today is what I'm going to call reconstructing words over some alphabet with a set of queries. So what do I mean by that? So there is a word W over this alphabet, and I don't know this word. But there is an oracle that knows this word, and the oracle will accept to answer some of my queries about these words. And so what I need to do is I need to choose my queries amongst this set queue of queries. So my task is going to be to try to guess the word W, to reconstruct it, by only asking queries from this set queue. And using the answer from the oracle, I want to be able to make this reconstruction. And obviously the goal is going to be to minimize the number of queries that I'm doing. And so what I'm going to do is I'm going to look at this general problem in a few contexts. Like I'm going to look at it in 4 different contexts, but this could be quite general. You could imagine different set of queries for which this is interesting. So for instance, there is this Wordle game that most of you should have heard of, where this is actually an instance of this problem. Only the set of words that you use is restricted to a subset of the English dictionary. But other than that, basically each question is a query, and then you get some answer, and based on that, you want to minimize number of queries until you guess the correct word. Okay. So what kind of queries are we going to look at today? Let me just define 2 more notions for this. So I'm going to say that U is a subword of W if it's a subsequence of W. And I'm going to say that it's a factor of W if it's a contiguous subsequence, right? I want to just insist on this so that, again, we agree on the definition. So ABA is a subword of BA. I can take A, B, and A, but it's not a factor of this word. Okay, so what are the family of queries I want to look at? So first, I could consider the following family of queries, which is I could ask to the oracle for any word U, how many times does U occurs as a subword in W? So I want to find all the occurrences of U as a subword, and I want to know how many of them there are. Maybe the oracle can answer this. A second family is, well, instead of asking the exact amount of occurrences of U inside of W, I could ask, is there at least one occurrence of U inside W? So that would be a second family of queries. Now, I could ask same thing, but for factors. So is U a factor of W? And finally, I could ask how many occurrences of U as a factor inside W. So these 4 different families of queries, they all give me a different problem, right? So for I can do the queries from this family, and I want to minimize number of queries that I have to make to guess the word, the unknown word W. Okay, so I will basically have 3 parts on this talk regarding the first part. I mean, the different parts will be corresponding to one of these families, and I will ignore the last family because it's a bit less interesting. So let's start with the queries which deal with factors. Okay, so let's make an example first. So suppose I have this unknown word W, and I know that it has length 9, and I want to try to guess it. So what we can do is we can try to build a long factor of W, and when I have a factor of length 9 of W, then this means that I have W, right? So maybe I can start by asking, is 0, 0 a factor of W? Maybe in this case, the answer is yes. So I was trying to, so yeah. So first I found the length of the largest block of 0. And I know that I have 3 zeros. Now, and this is the largest block of 0. And now I try to add a 1. The answer is yes, so I can keep going. I try to add one more 1 on the right. And then the answer is no. So as I said, let me repeat this. So it's not clear whether this is the end of the word. So maybe I had to stop there, or maybe there is a 0. For now, I'm going to assume that there is a 0, and I keep going. I try to extend by adding 1. Maybe the answer is yes. Okay, so I can keep going. I keep trying to add 1s, and now maybe at some point it's going to say me no, there is no 1. Again, no, and again, no. So I have 3 zeros which are hypothetical. I'm not sure that there is zeros there. And if I do it one more time, then there is something wrong, because now it's telling me that if I keep adding hypothetical 0, this would mean I have 4 consecutive zeros. But at the beginning, the first thing I did is trying to find the largest block of 0, which is length 3. So I know that there is something wrong. I reached the end of the word. So what I can do is I can try to find now where exactly is this end of the word. So I will try to add a 0 starting from what I really know is a factor of the word. Maybe I add 1 0, the answer is yes. I add a second 0, the answer is no. So now I know that I've reached the end of the word, and I can just try to extend on the left. And this is the same process. I will try to add a 1. If the answer is yes, I can add it. And if the answer is no, I have to add a 0. And then when I reach length 9, I know that I'm done, which happens to be the case there. I have a word of length 9, so this is the factor I was looking for, the word I was looking for. Okay, so I've used a particular strategy, which let me give the exact strategy that was actually given by Skinner and Sundaram for this problem in 95, which is the following. First, you can try to find the largest block of 0, and you do that by using a binary search. This is almost what I've done. This is a really short binary search, so maybe you couldn't see it, but this was a binary search. Now, what you're going to do is you will try to extend on the right, and when doing so, you will try to add a 1. And if it fails, you are going to add a hypothetical 0. Now, if at some point you added k plus 1 hypothetical zeros, then something is wrong, because you know that the largest block of 0 is of size k. So now you have to find the exact position of failure. And then when you've done that, you know a suffix of your word, so now you can extend on the left, and you will be done after some more steps. So what's the amount of queries you need to do if you do that? First, you need to do the binary search on I to find the largest block of 0, which is going to cost something like log n queries plus a few queries. And then for the 2 other parts, what happens? Well, whenever I do a query, I'm going to add a letter to my factor, which I'm trying to extend. And at some point, at this point in particular, well, I might need to remove k plus 1 letters and then to add each of them again. So basically, I have n minus k letters to discover, but I might need to do k other queries because of the position of failure, and then maybe plus 1 or plus 2 queries. Notice that if we were trying to do things a bit differently, so what we could try to do is, at every letter, we could try to add either 1 or 0. Like I could ask, is this correct to add a 1? And if the answer is no, then I could ask, is this correct to add a 0? But if I was doing that, then it would cost me 2 queries for each position. So I would have complexity 2n, when in this case, I have n plus log n. Something else I should mention is the fact that whenever I fail, again, what I'm going to do is, instead of doing a binary search to find the exact position of failure, I'm just going to add 1 more 0 to see if it works, and then 1 more 0 and see if it works. Again, by doing that, it means that whenever I'm doing 1 query, I'm adding 1 letter. If I wasn't doing that, then it could cost me a log n query to add only 1 letter. So that would be bad, because we really want to optimize it in a really precise way. Okay, so I have this algorithm from Skinner and Sundaram, cost me n plus log n queries. Okay, then Well, what you can notice is if you take a random word W, then the largest block of 0 shouldn't be really long. Actually, usually if W is taken uniformly at random, then the length of W is the length of the largest block of 0 is really close to log of n, like really, really close with high probability. So if you just do a greedy search, you start at at log n, and then if it tells you that there is a block of 0 of this size, and you try log n plus 1 and then log n plus 2, then the number of queries that you will do to find, that you will need to find the length of the larger block of 0 is actually going to be constant. It's bounded by 4 in expectation or something like that. So by doing that, you have an expected number of queries, which is n plus big O of 1. I think it's n plus 6, actually. And if you're really careful on the computation, you can improve it to n plus 5. But yeah, that's it. Okay, so we've proven that I didn't give the details, but we've seen that there is an algorithm that in average case takes n plus 6, and in the worst case, there is an algorithm for n plus log n. So what about the lower bound? Well, if you think about it, you could get the following lower bound, which is that there is no algorithm that can reconstruct W in less than n queries. And it's not that hard. Well, the first thing to notice is that every query has two possible outputs, right? It's either no or yes. So if the number of queries is bounded by n minus 1, then the number of possible outputs of the algorithm is bounded by 2 to the n minus 1. But the number of words of length n is 2 to the n. So I have a contradiction, right? I have less outputs than possible words to distinguish, so I'm not going to be able to do it. So I need at least n queries. And Skinner and Sundarm prove that n plus log n plus 2 or 3 is enough. In the average case, it's been proven that n plus 6 is enough. But there is still this gap of log n. So the question is, how much can we improve this? Is the lower bound optimal, or maybe it's the lower bound that is far from the truth? That's not quite clear, but at least what we did with Gwenaël, Richaume, we showed that this can actually be improved a little bit. So I'm not going to go into the detail of this particular one. In a few words, the idea is instead of starting your binary search, when you want to find a larger block of 0, instead of starting your binary search at n over 2, you start your binary search at root n. So by doing that, if the largest block of 0 is shorter than root n, then this is going to cost you log n over 2 to find the size, to do the dichotomy. Now, if the largest block of 0 is larger than this, then you're on a really, really particular case. Like there are actually really few, there are exponentially fewer words with a large block of 0, such a large block of 0. So we can try to use it to find a slightly better algorithm in this case. And so basically we have two different strategies depending on whether the length of the larger block of 0 is larger than root n or smaller than root n, and we can improve it a little bit. I believe that this can be improved even more than that, but we didn't manage to do it. Okay, so this was it for the factors. Now I want to focus on subwords, and I'm going to give some proofs in more details for subwords. I just wanted to speak up the factors a little bit because I guess it's a kind of a warm-up. Okay, so what about subwords? So again, let me just remind that I said a subword of a word W is just a subsequence of W, which I'm going to write like this. So for instance, 010 is a subword of 001101. Okay, good. And the question we want to look at now is, there is this unknown word W, and I can ask queries which are, is U a subword of W? How many queries do you need to be able to construct W? Yeah, so the first thing we can notice with the exact same argument as previously, every query has two possible outputs. Either, yes, this is a subword, or no, this is not a subword, which means that I need at least n queries. to be able to reconstruct W if W is of length n. I will assume that the length of W is known in advance. Doesn't make a big difference, but I will assume this. So how can you try to reconstruct a word W? Well, the first thing you can try to do is find a number of 0 in W. And this you can do with a binary search. You will, right? So you can ask, is 0 to the I a subword of W? And if the answer is yes, then it tells you that there is at least I occurrences of 0 in W. So you can do this binary search. So this costs you log n. And you know the number of zeros in W, and so this tells you that W looks something like this. There is a block of 1 of length that you don't know, might be length 0, then a 0, length of a block of 1, length you don't know, then a 0, etc. T times, where T is just a number of zeros. So now your goal is just to determine the value of each of these Si, and then you will know the word W. And for this, we can use the following easy lemma. So I know that W has this shape, right? So there are T zeros in W. And if I ask for the following, which is 0 to the I, 1 to the G, and 0 to the T minus I a subword of W, if the answer is, the answer is yes, if and only if G is smaller than Si. So why is that the case? Well, if you look at it, the number of occurrences of 0 in this word is exactly T. So basically, this when you look at this as a subword in W, this forces each of the 0 to match perfectly each of the other zeros. So now the 1, they have to be, so if there is an occurrence of this inside W, the 1, they have to be exactly between the I 0 and the I plus 1 0. So you know that if there is at least, if there is at least G1 between these zeros, then Si is at least J. So now that we have this, what we can try to do is we can try to use this to guess the value of each of the Si independently, one by one. So how would you do this? So we have this tool that allows us to, given some integer J, to check whether Si is larger than J. Hopefully some of you have guessed binary search. That was my goal at least. But this is not the good answer. The good answer is you should do it greedily, which is a bit surprising. So what do I mean by that first? What I mean by that is you should first try to ask, in some sense, is Si at least 1? Is Si at least 2? Is Si at least 3, etc. And by doing that, it's going to take you Si plus 1 queries to guess each Si, right? Because I will ask 1, 2, 3, 4, 5, and then I will have to stop at Si plus 1. Because Si plus 1 is going to tell me, oh no, Si is smaller than Si plus 1. And again, if you were trying to do it using a binary search, it could cost you log n to find only one letter, which is not going to be efficient. So now if we try to count the total number of queries with this strategy, there is this log n operation to find the number of zeros, and then I have to sum for each I the value of Si plus 1. But now the sum of the Si plus 1 for each I, so it's just the, if I try to do this, then S0 plus 1 is just the length of this bit, right? The first ones plus the 0. Now the S2 plus 1 is just the length of all these ones plus the 0. So what I get is the sum of Si plus 1 for each I is just n plus 1, because I have one missing 0 at the end in some sense. So this gives me the following, which is I need n plus 1 plus log n queries to do it. And more precisely, Skinner and Sundaram proved that you can do it in n plus 2 log n queries. And this is without knowing the length of the words, that you need 2 log n queries. Okay, so this is nice, I guess. Now, if we look at the upper bound, which is, as I said, given by Skinner and Sundaram, n plus 2 log n queries is enough to reconstruct the word. And on the other hand, we know that we need at least n queries. But I cannot say anything better than this. So there is still this gap of 2 log n. So can we improve this? Can we even improve it by a lot by doing something like n plus big O of 1? I don't know, even in the average case, I don't know anything to say about this. But now what we can do is we can try to see what happens over larger alphabets. This was for the binary alphabet. What about the larger alphabets? First of all, for the lower bound, it's exactly the same idea. There is 2 outputs for each query. So in that case, you need at least log of the number of words, and the number of words is k to the n if the alphabet is of size k, which is exactly n log k. Okay, so you need at least n log k queries. Okay, so using the result on the binary alphabet, Skinner and Sundaram proved that for a larger alphabet, it is enough that you have that many queries, 1.6 times n log k plus something. So, well, obviously, if you look at the lower bound and the upper bound, there is large gap there. So the question is, can you improve this, at least the first coefficient? Then we can try to see if we can improve even the rest of it. And the answer is yes, actually. You can really improve the coefficient. So the first term, the first order term becomes optimal. So that's what we did as well. So we proved that you can do n log k plus something. Now this something might not be optimal, right? So there is maybe a way to improve this. I don't know. So again, so what's the idea we used? For this one, again, I'm not going to enter into the details, but mostly the idea is, suppose you want to reconstruct a word over 4 letters. What they do first is they reconstruct a projection of this word over the 2 first letters and a projection of this word over the 2 other letters, and then they try to merge it. And when they merge the words, they do some binary search. And if you replace the binary search by some greedy search, then again, you can improve it. So like it's been a recurring theme that it's better for all of these problems in many situations to do a greedy search instead of a binary search, which is quite interesting, I guess. Okay, so let me now go to the main problem I want to consider today, which is the last family of queries I will consider. And for this one, I will give a bit more details. And I think it's a bit more interesting what I have to say. Okay, so let me first remind the context of this last setting. So I'm just going to use the following notation. So U choose V is just the number of occurrences of V inside U. This is a natural generalization of binomial coefficient. So for instance, 0, 0, 1, 0, choose 0, 1. So there is the first occurrence of 0, 1 and the second occurrence of 0. So this is 2. And now the question we are going to look at today is, for the rest of this talk. So you have this unknown word W. You can ask queries which are how many occurrences of U inside W as a subword, and then you want to minimize the number of queries that you use to reconstruct W. Okay, so let's do a short example just to have some intuition about what could be going on. Well, the first thing I could do is I could ask how many occurrences of 0 in W. And this is going to give me the number of occurrences of 0 in W. So I know that there are 3 zeros in W, right? Now I could try to find the number of 1s in W. Maybe there are 4 1s in W. I don't know. Sorry. This should be 2. So I want that there are 2 1s in W. Okay, so now I know that W is one of these words. I've listed all the words which contains 3 zeros and 2 1. There is a typo there. Now, how do we proceed? Well, I could ask this query maybe, how many occurrences of 0, 1 inside W? and maybe the answer is 4. So now we are not going to do it, but on the side I've computed the number of occurrences of 0, 1 in each of these words. And we can see that only 2 of them have 2 occurrences of 0, 1 as a subword. So we know that W is one of these 2. So now the next thing I can do is I can take one of these and ask, is there an occurrence of this word as a subword of W? If the answer is yes, then I know that this is W, and if the answer is no, then I need that the other one is W. So the answer is 0, which means that this one is W. Okay. So I guess from the start, you can see already that we will need less queries with this family of query because this is much more powerful, right? Instead of two possible values for the answer, we have much more possible values, and this will help us to be more efficient. Well, first, clearly, if I can ask, is you, sorry, the question, is you a subword of W is equivalent to does you occurs at least once as a subword in W, right? So clearly I can use the strategies that I had in the previous problem in this one. So I can do at least as good, right? This can be solved in n plus log n. If you remember what I did, it's even better than this because if you remember the log n was just to find the number of occurrences of 0, and we've just seen that I can find the number of occurrences of 0 in only one step. So in fact, just by this, you see that we need only n plus 1 queries with this family of queries. So Fleischmann, Lejeune, Mania, Novodka, and Rigo, they prove that you can do better than this. So there is an algorithm that constructs W in at most n over 2 plus 1 queries, which is better than n plus 1. So what's the idea? You can write, again, you can write W in this form. So it only costs you 1 query to get the number of ones. Now do you know that W looks something like this? And then you can find the SI one by one. Why is that? Well, there is a simple query that gives you the number of, sorry, that gives you SI. So you can just ask this query with, oh, there's typo again. So it should be 0 to the I, 1, 0 to the T minus I, which means that, no, sorry. Okay, it should be 1 to the I, 0, 1 to the T minus I, which means that I have T occurrences of 1. So so each of the 1, they are forced to synchronize with the T occurrences of 1 in this word when I'm trying to find it as a subword, which means that the 0 in the middle, that should be there, has to synchronize with one of this block of 0. So the number of occurrences of this factor is going to be exactly, of this subword is going to be exactly SI. But you can do much better than this. In fact, you can do it using only root n log n queries, which is much smaller than n over 2. And so the first part of the idea is the same. You're just going to write W in this form, but then it's instead of trying to guess the size of the block of zeros one by one, you are going to try to guess multiple block, and you need to guess something like root n divided by log n block at once. And how do you do this? Well, so I'm not going to do it in details, but I want to do it for at least 3 blocks, because the idea is actually quite technical, but if you do it for 3 blocks, I think you can get the main idea. So suppose I know that W looks something like this. There is a block of 0, a 1, a block of 0, a 1, a block of 0, and then a bunch of 1s. And what I mean is I want that the size of this factor is much longer than the rest of the word, and I'm going to use this. Now, if I have this, suppose I have this hypothesis, and I know the value of R. So I only have to, the only thing I have to guess is S0, S1, and S2. Can I do this in only one query? And I mean, you might be guessing if I ask the question, then the answer should be yes. And this is the query. So this is a simple query. I'm just going to ask how many occurrences of 0, 1 to the R inside W. Let's see why it works. So first of all, let's write the value of this. So what are the possible occurrences of 0, 1 to the air? Well, you have to choose the position for the 0. So suppose the 0 is inside this block. Then I have S2 possibilities for the 0. And all the air occurrences of 1 has to correspond to this air ones. Now, so this is the S2 in this sum. Now, if the 0 is in this part, then I have S1 ways of choosing this 0. And for the air occurrences of 1, I have air plus 1 occurrences of 1 there. So I have air plus 1 choose air ways of choosing these occurrences, which explain this part of the sum. And now if you take the 0 inside of this, then there is S0 ways to choose precisely the position of 0. And then there are air plus 2 choose air ways of choosing the ones. So you get this part of the sum. So this is the exact value of 0, the number of occurrences of 0, 1 to the air inside W. Okay, that's good. Let me write it like this, which is I've just written the binomial coefficient more explicitly. Now what I want to do is I want to express S0 in terms of the rest. So I'm just manipulating the equation. I'm just putting everything on the other side and then dividing by this quantity, which gives me the following. So it's just a basic arithmetical manipulation. Okay, so there are two parts of this sum. Let's look at the part on the right. So this part, remember that there is this hypothesis, which is that air is larger than all the SI. And by larger, I mean much larger, whatever this means precisely. But this implies that if you look at this, this is SI, some SI, and this is air times some SI, and at the bottom you have air squared. So this should be much smaller than 1. Okay, so this is much smaller than 1. But now there is something interesting. We know that S0 is an integer. So in fact, this implies that S0 is simply this taken to the nearest integer. Not the nearest, but the, how do you say this? The flooring, yeah. So S0 is simply the flooring of this quantity because this is something which is between 0 and 1. This is an integer, so it has to be the flooring of this quantity. Okay, now this is the query we've made, so we know the value just by the result of the query, and by assumption, R is known. R is known by the assumption. So we can recover the value of S0 thanks to this query. Now let's try to do the same thing for S1. So again, if I'm taking this equation, I'm just rearranging everything. I obtain that the S1 is can be written in this form. Now again, S2 divided by R, it should be much smaller than 1 by assumption that R is larger than SI. Again, S1, it is an integer, which means that I can take the flooring of this part, and I get the value of S1. Now, if you look at this, all the values are known. This is the query. R is known by hypothesis, and S0 has been computed in the previous line. Okay, so now we know everything. We know S1, we know R, we know S0. We know the query. The only thing that we don't know is S2, but now it's pretty easy to recover S2 from the fact that we know everything else. So we can recover the value of S0, S1, and S2 just with one query. And in fact, this idea can be generalized and we can be more precise on what we mean by R much larger than SI in such a way that we can recover much more block of zeros with only one query with some hypothesis. And this can be written in the following lemma. So suppose I know that W looks like this. So basically the only thing I know is how many zeros, how many ones, sorry. I know how many ones I have in W. And moreover, there is this extra hypothesis, which is that I fix some integer n, and then for each SI, I know that it's smaller than m, or I know the exact value of SI, which is a strong hypothesis, but somehow this is equivalent to what we had before, which is that all the SI are small enough. So this is a generalization of this idea. Now, under this hypothesis, I can reconstruct fully W using only 4 M queries. Okay, so there is something missing there, which is I need to know the value of all the SI which are larger than M. How can I do that? And there is another lemma which I'm not going to detail too much for this. But again, if we know W, then this set I can be computed in that many queries. So the idea behind this lemma is to do some kind of binary search. Like we want to localize the part of the word where there are many zeros. So we can split the word in half and ask, do we have many zeros on the left and do we have many zeros on the right? And sometimes the answer can be yes in both sides, which means that our binary search should go on the right and on the left. But this cannot happen too much because the number of zeros is bounded, so there cannot be too many places where there are a lot of zeros. And so this is how we get this complexity. I think that the idea is cute, but I cannot go into details. But somehow by doing this kind of generalized binary search, we can find efficiently all the large block of zeros and their localization. So now we have all the tools. How does it work? First, I can compute the number of zeros and 1. I only need 2 queries. Now I can find all the large block of 0. And again, large means larger than M. We'll see what it means a bit later. And by the second lemma from the previous slide, I need that many queries. Now I can compute the remaining SI, which is going to cost me 4 M queries, and then I'm done. I know the word, I know the value. So obviously there is something to optimize there, right? Because if M is really large, then this is going to be expensive, but if M is really small, then this is going to be expensive. So what is the best value of M? Well, you can take M to be something like root n log n. So you could optimize a little bit more, but say you take M to be root n log n, then the number of queries on this part is going to be root n log n, big O of root n log n, and the number of queries on this part is going to be big O of root n log n. So in the end, if you choose M to be root n log n, you can prove that the number of queries that you need is big O of root n log n. Okay, this is nice. There is something. So first of all, let me say already right now, I don't think this is optimal. And in particular, there is something a bit annoying, which is again, somehow I'm searching for block of zeros of size root n log n, and this costs me a lot. But as I said earlier, we know that in expectation, if I take a random word, the largest block of zero should be much more than that. It should be of length log n. So there is something that should be suboptimal there. In particular, if we look at the average case, we can do much better. So let's try to look at this. So as I said, if you take a random word, then it shouldn't contain large block of zeros. More precisely, I can give the following statement. So if I have the word W, which is taken uniformly at random amongst all words of length n, then the probability that I have a block of zero of length 2 log n is less than 1/n. This is really easy to prove if you know really the most basic probability. You just, if you look at a given position, the probability that it starts with a word with a factor of length 2 log n is at most 1 divided by n squared. And then if you use union bound to sum over all the positions, then you get that the probability of this is less than 1/n. So it's like a 3-line proof or something like this. So this is going to be quite convenient. The large block now, instead of being root of n log n, we can take it to be log n, which is much smaller. And so we can improve our algorithm as follows for the average case. First, we will compute the number of zeros and 1, which means we need 2 queries. Now, instead of trying to find the large block of zeros, we will simply pretend that there is no large block of zeros. Let's just pretend that there is no such block. Now, since I have no block of length smaller than 2 log n, by the previous lemma, I only need 4 times 2 log n queries to compute the remaining Si. Okay, now there is something wrong, which is maybe I was wrong when I pretended that there is no large block of 0. So I have to check if the W I've found is correct. For this, I need only one query, right? I can ask, is this word of length n a subword of W? And if the answer, if there is one occurrence, if there is one occurrence of my candidate inside W, then this means that this is W, otherwise this isn't W. So if the answer, if I learn that I was correct, then there is nothing to do. I'm done. I've found W. Now, if I'm wrong, then I can just apply the previous algorithm. And this is fine because I'm going to be wrong with a really small probability, with probability 1/n. This is what we've seen on the previous slide. So I don't really care about how much it costs me, since I'm only interested in the average complexity. So if we do the computation, basically, in every case, I need 2 queries plus 8 log n queries plus 1 query. And with priority 1/n, I need that many queries. So in total, this is 8 log n plus big O of 1. So what we get is that in the random case, so there is a deterministic algorithm that in average, given a random uniform word W, reconstruct W and expected number of queries, which is big O log n, which is much better. Okay, so let me summarize this. So somehow the previous result for the worst case complexity and the average case complexity was that n/2 queries are enough. But we're able to improve it to prove that in the worst case complexity, root n log n queries is enough, and the average case, big O log n is enough. So what about the lower bound? Well, I don't know. I don't know anything about the lower bound. This might still be far from optimal. Actually, I don't even know how to prove that you need at least 20 queries if n is large enough. It's probably doable, and I don't think it should be constant, the number of queries that you need. I think it should be an increasing function of n. But I don't know how to prove anything. I don't know how to prove log n or something like that. Now the other thing is, it seems that this should be optimal. Like the gap between the worst case complexity and the average case complexity is huge, which is really weird. Like that would be really surprising that this is optimal. This shouldn't be optimal. So there is probably a lot of margin to improve this one. I don't know how to do it, but there should be a way to do it. Okay, and maybe even this one might be possible to improve it. This one I don't know, and I wouldn't conjecture anything, but yeah. So I don't know. Okay, so let me conclude on this. So when I think generally this question about word reconstruction, given some queries that you can ask to an oracle. So it's been studied by a few people. The original motivation comes from biology. I didn't mention them, but like there is this question of DNA reconstruction and stuff like that. I think there are a few nice questions which didn't receive that much attention, and that might be not that hard to solve if you spend the time on it. So there are a few interesting questions that deserve a bit more attention, I think, in this setting of word reconstruction. Yeah, let me mention some results in this vein. So there is this result by Fici, Preza, and Venturini, a quite recent result, where they prove something. So basically, they prove that if a string is compressible, then there is an algorithm that reconstructs this string more efficiently using substring queries, which is what I called subword queries. So there are links to other problems in how do you call this, compressibility things. Okay, so there are a few interesting questions. They are the one I mentioned during my talk. And what I want to end on is something else which is quite interesting to me, at least, is there is a good lesson there, which is binary search is sometimes worse than greedy search, which at least for one of the algorithms, really, we improved it by quite a lot. And simply what we did is replace a binary search by a greedy search. And just doing some analysis of it, but the analysis was not even that complicated. It was actually easier than analyzing the binary search. So yeah, this was quite nice. Okay, and I want to end this, so thank you for your attention.
Oh, thank you very much, Matthieu. Does anyone have any questions? Oh, yeah, Hajime.
May I see the page 21?
21. Yeah.
So what are the case where alphabet is alphabet has K letters?
Right. I don't remember. What about the case where the alphabet has K letters? I don't think we've. Oh, right. Yeah, so one thing you can do is if you know so if you know so suppose my word is on 7 letters, I don't know, and you know all the projection on 2 letters. You know the projection on 0, 1, you know the projection on 1, 2, the projection on 2, 3, etc. You know all of them, then you can reconstruct the word. In fact, you don't need all of them. You need some of them. I don't remember how many, but you need some of them. And so you can just choose it. You just use the binary reconstruction because you can just ignore the other letters when you use our idea, and you obtain something which is better than the previous one, but it's just better because of what happens on the binary alphabet. But it's exactly the same strategy for larger alphabet. There might be something else that you can improve even more on larger alphabet, but we didn't look into it.
Okay, thank you.
Oh, there's a question in the chat.
Can I see
for the factor queries, what happens if the alphabet has K symbols?
Yeah, so I didn't mention it because we did nothing on this, but let me just go back for everybody. So this is this last case that I mentioned there. Then no, sorry, K symbols. For the factor case, yeah, I didn't mention it either. I don't remember actually. This is a good question. I don't remember. Yeah, okay. So if the alphabet has K symbols, somehow you need to do the best we know how to do is a similar strategy, which is you start by asking if the next letter, if you try to extend on the right and you ask, is the next letter a 0? And then if you know it's not a 0, then you're going to ask, well, then is it a 1? Then is it a 2? And simply, if you get an answer which is no for each of them, you're not going to ask the last one. Like suppose my alphabet is 1, 2, 3, 4, 5, 6. Then when someone tells you no for 5, then you're just going to put a hypothetical 6 and keep extending. But then somehow it's not, I mean, so you get something which is slightly better than just trying all the possibilities, but it's really just slightly better, and it's not clear whether we can do better than this or not. So the gap, I think, is quite large when the alphabet is large between the lower bound and the upper bound. It's something like the lower bound should be k log n, and the upper bound is k minus 1. Sorry, k minus 1. Yeah, okay, I don't remember. Sorry, I'm just gonna say it in top of. Yeah, sorry, I cannot remember exactly, but there is a big gap, I think, in this case.
Stefan?
Yes, hello. My question is whether you have used anywhere in your work the concept of entropy of the word, because it seems that it should be the right measure,
Yes.
for example, for having a lower bound.
Yeah, sure. You're right. Where is it that I give the lower bound? So this argument that I've given there, saying that you need at least n queries, you can use entropy instead of really counting what happens, and then you obtain that even in the average case, you need at least n queries. I didn't mention this, but it's just using entropy, and it's just, again, it's like a 5 or 6 line proofs, and then you get that even in the average case, the average number of queries you need to do is at least n. And so it's the same thing for the subword queries. Now for the one that is really completely open, this one, which is completely open, I don't know what to do with entropy. Like, the thing is, some of the queries you could try have a really, which way is it? Have a really high entropy, gives you a lot, could give you a lot of information, but then it seems to be the case that if it gives you a lot of information, then you have the set of words that remains possible. Somehow they have a really bad structure, so you will need a lot of queries to do something, but it's quite unclear what happens. So really, I don't have any idea what is the correct lower bound. I don't know if it should be log n or much smaller than log n. I have no idea. I guess it shouldn't be constant.
I mean, at least
even tell that.
At least you said that you don't even know whether you have a constant, whether it's not constant. So it seems that it should be somehow easy, but I don't have any immediate answer.
Yeah, I really tried to think about it using entropy, and I didn't manage to do it. But I encourage you to do it, definitely.
And another concept, of course, related is Kolmogorov complexity, which you also kind of mentioned. So I think one of these should give you some lower bound, but I don't have it immediately.
Yeah, that might be true, and I tried to think about it this way, and I didn't manage to do it. But I'm not an expert on none of these two notions, so maybe there is something to do there.
Okay, maybe there is somebody.
Hopefully, someone is going to prove that this is non-constant using these tools.
Somebody. Yeah, I think that should be something in the direction. Thank you.
Thank you.
There's a remark in the chat. Each query gives at most log n bits of information, so needs at least n over log n steps, right?
No, that's not true. That's not true. I mean, first of all, we've proven that you can do it in log n, so you need less than n of a log n step. But really, because the number of occurrences of u inside w can be much more than the length of w, right? It can be a really large value. We are looking at subwords, not factors. So number of occurrences could be close to what is it? 2 to the root of 2 to the n or something like that, right? So the number of occurrences of 0 to the I inside 0 to the 2i is 2 to the I, right? So that's really bad in some sense. If you want to obtain some bounds using just this, you need to be probably a bit more precise.
All right. Are there any other questions for Matthieu? If